What we're doing this morning is we're talking about weight and balance. And weight and balance, there's a few things you want to know about it. And I guess one of the things is how to do it if you're going to build an airplane. If you buy an airplane that's already been manufactured, they'll do the work for you. But if you build something, you got to figure the weight and balance yourself. What we're going to do this morning is a weight and balance on this aircraft. Jim and I have already done a lot of the footwork because it's time consuming. We've spent about 2 hours on this aircraft setting it up. And we're just going to walk through it and show you how we did the weight and balance. To start with, all aircraft are sensitive to weight and all aircraft are sensitive to balance. And weight is the forces acting on the airframe and also affects the lifting ability of the wing. Balance is your ability to control the aircraft. So you've got to consider both of them. When they design an aircraft, they design it with a maximum weight in mind, and you don't want to exceed that, or you're going to overstress something in the aircraft. And the balance aspect of it, if you want to keep control of the aircraft when you're flying in all aspects of flight, you might have it out of balance, and flying it in cruise, you're okay, but if you slow the aircraft up, it might not handle properly. So you lose control. You want to understand the relationship of weight and balance to theory of flight, because there is quite a relationship there. For instance, in a 60-degree bank turn, which you could do quite easily with a small aircraft, you experience 2 G's on the airframe, twice its weight. So if you have a 1,200-pound airplane, which is an ultralight, you would be putting 2,400 pounds of force on that airframe. Also to think of is in 2 G's on the aircraft, mathematically worked out, you'll increase the stall speed of that airplane by 1.4. And if the aircraft stalls at 40 miles an hour, you've increased the stall to 56. And that gets into the balance aspect of the aircraft. If you have it slowed up, your center of gravity is out, you do a steep turn, you approach and stall the aircraft, you could go into a spin or an incipient spin, and if the aircraft's out of balance, you won't be able to recover. We started out with the scales. Try and get scales that, if it's ideal if you can get a scale that's been calibrated. If it hasn't been calibrated, try and calibrate it yourself. Get some weight that you know of and try it on the scale and make sure it's accurate. So we did that with all 3 scales, and then the next thing we did with our scales was we zeroed them to make sure that we're starting off at 0 when we weigh the aircraft. The hangar floor is level and it's swept off, clean. Try and do it, do your aircraft in a hangar when it's not windy. You want to make sure the aircraft is in flying attitude. Now this particular airplane, you lift up the tail and you put a level on here and get it into a level attitude, a flying attitude. So we had to do that. If you look back at the scale, we had to set the scale on a table, and then we had to put some blocks on to raise the tail up. For the scales up here, to get the aircraft on the scale, we lifted the aircraft up, sat it on the scales, and then we blocked the wheel so it won't roll off. The one thing we're going to have to keep in mind is when we start doing our calculations is that we use some blocks here to keep the aircraft from rolling around, so that's a tare weight, and we're going to have to subtract that off of the figures that we've got here. And the same thing back here. We've got a couple of blocks of wood, and we'll have to take that off our weight. When you weigh an aircraft, you've got it sitting on scales, don't have the brakes on. You can put like a force onto the scale, just like putting brakes on a car. You know, you have a torque that's put on the wheel, on the axle, and it could be acting on the scale, and it's going to throw your weight off. So that's why you want to have it chalked up so it doesn't roll around on you, but you don't want to have any brakes set. When you weigh the aircraft, check, for instance, if you have something that's liquid cooled, so you make sure your liquid coolant is topped up, your oil is at a level it's supposed to be. You want to drain all the fuel out so you know where to start as far as using your weight and balance. If it's a two-cycle engine and you have an oil injection system, you want to make sure that that particular tank is either topped up or empty. You'll get into trouble, and same with the fuel tank, if you go halfway in between. You don't know how much fuel's in the tank, you just look at it and say, oh, it's half a tank. Well, you'd be better off to drain it out or fill the tank up completely, one or the other, but don't go halfway in between. Same with your oil and the coolant. If you have an engine coolant, make sure it's topped up. Another thing to think of when you're doing the weight and balance is you want to make sure that everything is cleaned out of the airplane. For instance, this aircraft had some tie-down chocks and some ropes and stuff in the back. You want to clean everything out. You want the aircraft to be as clean as possible when you're going to weigh it. Because quite often aircraft are designed that if you fill them full of fuel, in this particular aircraft you can carry a passenger. If you put a passenger in it, it also has a baggage compartment. You fill the baggage compartment to its maximum capacity, you can overload the aircraft. And they design it that way so as a pilot you can manipulate things around. If you got it loaded up, you can maybe take less fuel to keep the gross weight down. I would say most aircraft, when you load them up completely, will be over gross weight. So you have to keep that in mind when you're doing your calculations to fly. So we set the aircraft up on the scales, and we weighed each particular wheel. This wheel ended up being 318 pounds. This one over here was 315, and the back was 53.5. When we weighed these wheels, you'll notice there's a bit of a difference in weight between the left and the right. And that's very common to encounter in a light airplane or in any aircraft, that they don't weigh, both of them don't weigh exactly the same. Now, if there's a big weight change, like we've got, say, 20 pounds between one and the other, you might want to look for a reason why there is. Is it something that's been installed in the aircraft in one weighing, say, a wing tank in one side and not in the other? Or maybe be a little suspicious of your scale, that your scales are giving you a false reading. But it's not uncommon to have a few pounds difference between left or right. If you've weighed a lot of different small aircraft, in this one in particular, you look at the weight of the tail, and 51.75 pounds is quite common. You'll have a light aircraft that might have anywhere from 40 to 65 pounds for a tail wheel weight. That's fairly common. So we got the weights, we wrote them down. The next thing we have to do is figure out a datum. And a datum is a point you've picked somewhere on the aircraft that you do all your measurements from for a distance. And we've decided to use a datum that is 4 feet ahead of the leading edge of the wing. You could pick a datum point anywhere you want on the airplane. Some people do. Some people actually do pick the firewall. And some people pick the leading edge of the wing. But you want to pick an area that is not going to change. For instance, if you picked something on the engine mounts will wear after a while. And so they could change. Same with the landing gear. So it's quite common to use the wing leading edge or the firewall. But when you pick a datum, like this is our datum point here. Okay, when you pick that datum, like you use it for all your figures. Now, if you want to pick another point, you can. But we used 4 feet ahead of the wing leading edge, and the idea behind it was, if you were to drop this down, right, you would find that your datum is ahead of the airplane. Okay. And the reason for having it ahead of the airplane is the mathematics. Anything that is behind the datum, or that is ahead of the datum, is a negative number. Anything behind the datum is a positive number. So if you start dealing with positive and negative, and you're not really strong at mathematics and memory, you'll end up making a mistake, and it's very easy to do. So that's why we used like the datum so far forward, and we used it from the wing leading edge because we can always find it in the future. You know, like we know where this is. To find our center, we took a plumb bob, found the center of the airplane, made a mark on the floor. We went back to the tail, did the same thing, and then we took a chalk line, joined the two, and then we started measuring all our distances of what we really need to know. We need to know the distances of our landing gear, our tail wheel, the chord of the wing, the pilot seat, the passenger seat, our fuel tank, and our baggage area. This aircraft does have a baggage area in it. So we went ahead and we used whatever means we could. We stretched some string from axle to axle and dropped our plumb bob down. We found where the axle mark is, made that mark. We went back, we did the same thing on the tail. And we marked it on the floor, and then we measured back to the center of our axle on the tail wheel. The wing chord length, when it was measured out, I took the plumb bob and I dropped it down, and I took a measurement of what the chord of this wing is, okay? And the chord of the wing worked out to be 62 3/4 inches long. The pilot seat was a fairly easy one to do on this aircraft. We just opened the door. We had a look inside, and we basically picked the part of the seat which is, as you're sitting, the back of your butt was considered the center of the seat. We dropped that line down, and we found the distance to be 74 3/4 inches back from the datum. Remember, everything's being measured from this one point, okay? Passenger seat, this aircraft is side by side, so it's the same measurement. We found out where our fuel tank is located. We measured that, and when we measured it, we went from the datum here, and we measured back to our mark for our fuel tank, the center of our fuel tank, and it was 38 3/4 inches. How do you determine the center of your fuel tank? We had a look in the cockpit. We measured the tank itself, and then we measured its distance from the firewall, and then we dropped a line from the firewall down and did some calculating. So there's a lot of small calculations that are involved to find out where things lay, and it's very easy to make a mistake, so that's why you want to like double check things. The baggage area, we looked inside and we found that the baggage area starts right here. Okay, and the baggage area ran back 27 inches, I believe it was, Jim. And so we dropped a line down on each side. We found the front of the baggage, marked it down, went back and marked in the center of the baggage area. The wing leading edge, we wanted to know that, so we dropped the plumb bob down again. And we did that on each side of the wing. We ran a chalk line through. As you can see, it's kind of hard to work with the scale, so we ran our chalk line underneath the scale, and it worked out quite well. We also marked a few other things just for future reference. We ran a line down from the back of the flange on the prop, which is something that's not very useful to us today, but for somebody in the future, they have a reference. We also marked the firewall, and again, we're just recording that for future reference for someone. If they're adding or something, or taking something off the aircraft, they have an area to measure from. It's easy to measure, rather than going through a whole weight and balance again. So now we've got all our measurements, and we can start doing some calculating. Our datum line was 48 inches ahead of the wing leading edge. We want to record our wing chord length, which we wrote down as 62 3/4 inches. Our wing leading edge from the datum, well, it's 48 inches. Our left wheel came out to 318 pounds. Our right wheel came out to 315. And our tail wheel, in this case, came out to 53.5. Next thing we want to do is we want to weigh up the tears off of all of our scales. So we'll take and we'll subtract that off our figure there. $315.5 plus 312.5 plus 51 3/4. Okay, so that's the empty weight of our airplane. 679 3/4 pounds. Your arm times your weight equals a moment, which is a rotational force. So your arm times your weight equals the moment, or your arm equals your moment over your weight, and that would determine a center of gravity. So from there, we're going to start and show you how we did this particular aircraft. So we got 47 3/4 times 315.5 equals 15,065, 14,921, 11,242. So far, so good. Our next step is we add up the weight, which came up to 679 3/4. And we add up our moments, 41,228. Another thing to keep in mind is keep all your measurements the same. Like in this case, we're using inches and pounds, but you could go metric. So this is what we came up with for the aircraft empty. It weighs 679 pounds. The moment is 41,228. We don't really need to know the arm or the center of gravity because, like I said, the airplane as it sits there, you can't fly it. You got no fuel, you got no pilot in it. So these are the next things we want to calculate in. And we had our figures. Our fuel tank was 38 3/4. Our baggage area was 96 inches. Our pilot seat was 74 3/4, and so was the passenger. We got the arms in here, so all we got to do now is we can sit with our calculator and we can play with weights to see what's going to happen. In this case, if we start off with a standard weight pilot, which Statistics Canada, and it's also in your AIP if you happen to look in that book, the standard weight for a pilot in Canada is 200 pounds. So the pilot's 200, passenger takes along, say it's an instructor, and takes along a female student. Average female weighs 165 pounds in Canada today. Baggage, they have a posting in there of 40 pounds. So let's put 40 pounds in it. Our fuel, 12 US gallons. A US gallon weighs, if you go back to the AIP or the Canada Flight Supplement, 6 pounds. So 6 12s is 72. Now we need to do the math to add all this stuff up. So we did a little bit of calculating here. We took and we multiplied our weights times our arms. We add up our moments, add up our weights. If this aircraft has a maximum gross weight of 1,200 pounds, So we're 1156. We added up our moments, came to 75,142. We want to know where the center of gravity is on that airplane with loaded the way it is right there. Is 64.9 inches back from the datum. 65 inches back. Right at the end of my tape is where the center of gravity, that's where that aircraft should balance when it's got full fuel. So we know and we can see where the center of gravity is. But what's that going to do for us? Because it's the wing that's doing our lifting. I've taken a wing rib here just to give you an idea of what it's like to look at the side of a wing. And basically, you want to have your center of gravity fall within this range here, 18 to 35% of this wing rib when you're flying. That's an accepted norm for a center of gravity on an aircraft. I've marked it off. Okay, there's 18% and there's 35. You want the center of gravity to fall within that area when you're flying it. So you got to sit down and we got to do a little bit more math. We got to figure out on this wing where that's going to be. If it's 62 3/4 from here to here, you want to find out where 18 to 35% of that is. So you start doing a little bit of mathematics again. 62 3/4, 18% of that is 11.3 and 22 inches. So if you want to physically look at the chord of the wing, it's anywhere from 11 to 22 inches back is where the center of gravity should lay. So anywhere from this point here to this point here is where the center of gravity should lay on here. But we haven't gotten that far yet. We don't know. We've got to figure out where that is from the datum. The leading edge is 48 inches back. Okay, so our center of gravity had to lay anywhere from 11 inches to 22 inches in that chord. So you add 48 onto those two numbers. When you work it out, when you add 48 onto 11.3 and 22 onto 48, the center of gravity should be 59.3 to 70 inches from the datum. 64.9. So are we good? So your center of gravity is good, and your gross weight is good, and I am actually quite amazed because you've loaded this airplane up pretty good. You know, like you got 40 pounds of baggage, you got 2 standard Canadians in there, male and female, and you got full fuel, and you're under gross and you're within center of gravity. This is a good airplane. If we don't get our center of gravity to fall within the range that we've decided it should fall within, then you're going to have to sit back and look at the airplane and see, okay, what can I change? Like, can I move the baggage area? Can I move the seats? Can I move the engine, fuel tank? And if I can't, then on some aircraft you'll encounter, even on some commercial aircraft, they'll put ballast in to bring the aircraft back within center of gravity, an acceptable center of gravity. Now, if you start adding ballast, you gain one more problem. You're adding weight to the aircraft. So if the aircraft weighs, say in this case, 1,200 pounds, is a maximum weight that you want that aircraft to weigh, and you start putting ballast in it, when you throw 2 people in it, say an instructor and a student, who both weigh 200 pounds, how much fuel can you put in it? And you do need a minimum amount of fuel to be flying around. And as you fly the aircraft, depending on where the fuel tank is located in the aircraft, how's your center of gravity going to change as you fly, as you burn up fuel? Because you've, say, burned up your fuel, the center of gravity has changed, The aircraft might be put into a situation where your ability to control it is questionable, and you're coming into land at a low airspeed. And like I did there, if you start making a steep turn, you approach the stall, the aircraft becomes unstable, and you stall it. Can you get back out of the stall? You know, and that's one of the reasons for calculating the center of gravity, to make sure you can control the aircraft in all aspects of flight.